Question 1. The activity of a radioactive sample was measured over a 6-hour period. The results are recorded in Table 1 below. Part A. You're to use the grid that is provided on the exam paper to plot a graph of activity A versus time T. Let's get into it for 8 marks. So first thing you should do is to put a title. You get a point for that. Then label your axes. Time T in hours, activity A in disintegrations per second. Then you should choose a suitable scale and state it on your paper. So in this case, the horizontal will choose a scale of 2 centimeters to 1 hour because our data went up to 6 hours. And for the vertical, we'll choose a scale of 1 centimeter for 5 disintegrations per second because that data went from 0 up to 80. So when you number your horizontal, it's basically like you skip and then you number. You skip and then you number. So it should look like that. And then for the vertical, you're basically counting in 5s. Then your next points come from your plotting of the points accurately. So we have 0 with 80, 1 with 50, 2 with 34.5, 3 with 20, 4 with 13, 5 with 7.5, and finally 6 with 5. So whenever CXC grades, you get all points, 4 points for the points plotted accurately, if all of them are plotted accurately. And for every 1 or 2 that is incorrectly plotted, you get 1 point off. The next point, the final point in part A, is to draw a smooth curve that goes through as many of the points as possible. So it's a decay curve, so it should look like a curve that goes down like that. And in this case, it won't pass through all of the points, but most of them. And later on, we'll see why it doesn't pass through all of the points. Then, part B, part 1, to determine a value of the half-life. So half-life is the time that it takes for the activity to drop to half of its previous value. So at the beginning, at time 0 hours, the half-life was 80. How long does it take to drop down to half of 80? Well, half of 80 is 40. So you get a point for drawing your dotted lines on your graph, starting at 40, going horizontally till you meet the curve, and then coming down. Please note that I have drawn a solid line because, of course, I did this on a computer, and it would have been very tedious to draw the dotted lines, but when you do it, please make sure that you do not draw a solid line, draw dotted lines, okay? If you draw a solid line, you risk losing that easy mark. So make sure that the lines that you draw are dotted. So 40 corresponds to a time of 1.1 hours. So then the half-life would be 1.1 minus 0.0, which would give you 1.1 hours. Part B, part 2, asks then to determine a more accurate value of the half-life. So to determine a more accurate value, you would do multiple half-lives and find the average. So we're just going to do one more. So we're going to find half of 40, which is 20. So you would start at 20 on the vertical axis and go over horizontally till you meet the curve and come down, and you would read that corresponding value. So then the half-life would be that value of 2.9 minus the previous time that corresponded to 40, which was 1.1, and that would give you 1.8 hours. So we now then will find the average of the two half-life values that we have estimated from our graph. So the average will be 1.8 plus 1.1 all divided by 2. So that works out to 1.5 hours to two significant figures. Part C of the problem then asks you to find how long it took for the activity to drop to 10. So you start at 10, go over horizontally and come down, and that corresponds to a time of 4.5 hours. Part D of this question says, state one reason why a line drawn through all the points would not form a perfectly smooth curve. So one reason why a line drawn through all the points would not form a perfectly smooth curve is because there are always experimental errors, in this case, such as background radiation, which may affect measured values. Part E All elements, including radioactive substances, have an atomic number and a mass number. Explain what these two terms mean. Well, the atomic number is the number of protons in an atomic nuclide, and the mass number is the total number of protons and neutrons in an atomic nuclide. Part F. In medicine, iodine 123 is used to check a patient's thyroid function. What does the 123 represent? Well, the 123 is the mass number. And that's question 1 for 25 points.